Hello and welcome to session 241 in the AISafety.com reading group. Tonight we will be discussing Fine-Tuned Language Models are Zero-Shot Learners by Jason Wei and others. This is some research done by a team in Google Research with Jason Wei as the primary author and Martin Bosma as the person who conceived the idea and implemented the first version of the actual model. And there are a number of other primary authors and a list of secondary authors. It's a preprint from September. They describe it as fine-tuning language models on a collection of data. It's described via instructions substantially boosts zero-shot performance on unseen tasks. So let's zoom out a bit first and discuss what is the relationship between this and AI safety, because the connection is not entirely obvious, and they don't write anything about AI safety almost. So we had the language models are few-shot learners, the GPT-3 paper a long time ago, where when we presented this, or I presented this almost 2 years ago, I made a comment on that, and that is, can you fine-tune GPT-3 to be more aligned? I don't think that was very original. A number of other people almost certainly must have thought the same thing, but a lot of people, very few people actually pursued this. Some people have started to do that over the past year or something like that, but that's something more new. And aligned, of course, is the property that we're interested in. And there are a number of properties that a language model can have or can't have. And it's not really obvious a priori what properties it will have. An example of a property would be like, is it mathematically precise in its, is it logical or is it more poetic? And if you look at the actual GPT-3, it's certainly more poetic than precise. So a way to split up alignment in 3 parts is it honest, is it harmless, and is it helpful? So those are 3 properties that a language model could have, and it's worthwhile to investigate. So can it be honest? Well, honesty seems to be a property that doesn't map well into language models. Like, there is some work being done on truthful QA. Some work is being done, but it's certainly not obvious. And you see sometimes that as the model gets smarter, it is more likely to tell you that breaking a mirror results in 7 years of bad luck. Harmless is harm a concept that is natural for language models? Not really. There is some work being done, for instance, by Redwood Research to try to see whether it is in fact possible to make a language model fine-tuned in a way so it doesn't talk about violence, but it's not obvious. Can you make it helpful? Well, that's really what this paper is about. Instruction following is quite close to helpful, and so when I'm not entirely happy about this seeing alignment as a combination of these 3 features. I'm not sure it's a good model. I think it's either, I think it's Paul Christiano's framing, might also be the Amadeus. I need to look that up, I think, because I feel on reflection, helpful seems like the kind of thing that people care so much about that it's going to be done by default. So I think even if it was not very helpful, there would be enough optimization pressure put in that direction that it probably would end up being helpful, or otherwise it wouldn't be deployed as much. Right, so let's go back to language models and their limitations. We've seen obviously that if you take a language model and just deploy it without any other work, then it's not that good compared to how much it costs. It needs some kind of hints about what it should be doing. That's sometimes called few-shot learning. So it needs a few examples and it's also something that doesn't really happen until the language model is quite large. The authors speculate that this could be because the thing that it's been trained with and the prompt formats in the tests are quite different. It's unlikely to see precise kind of way of talking in the 45 dB that GPT-3 is trained with. So you can see here in with GPT-3 you have pre-trained language model, and then if you want to do inference on some kind of task, then you can give it a few examples, and you can try to change the prompt in different funny, interesting ways. Prompt engineering sounds better than prompt hacking, but that's basically what you can do, or at least the way it's written here. I think the authors almost certainly know it, but GPT-3 certainly can be fine-tuned. So you can, even though they say this is like the GPT-3 way, you can do more things with GPT-3. And the alternative they're saying is that you can pre-train and then fine-tune, where you perhaps somewhat laboriously find some examples of maybe like 100 or even more, as many as you can get, to fine-tune the model on these. And then you get a specialized model that is substantially better at one task. And the reason why we feel this helps is that it feels very often like the models, in some subjective way, it seems clear that the language model itself, it knows the answer to the question that we are given, but it's just we need to either prompt or fine-tune in order to make the model want to give us this kind of to follow our instructions, basically. Let's talk about instruction tuning, the new kind of fine-tuning that the authors are proposing and implementing here. So they take 62 natural language problems, and they change those into natural language. So we'll get back to how to change a natural language problem into natural language, and then you get some natural language that you can then fine-tune on. So that gives you a different option where you have a pre-trained language model, and then you fine-tune it on a lot of tasks, and then that makes it, of course, better at the task you fine-tuned it on, but also at following other kinds of instructions. They call this the fine-tuned language net. It's somewhat of a strange name in my opinion. As far as I can tell, there's nothing more net-like than the other kind of transformers that we're seeing. And I think fine-tuned is not that descriptive name. It would be more interesting to see like it's instruction following. It would be my suggestion for a name. And so they show that this does indeed improve zero-shot performance very much, and also that this is something that that only happens with large models. One important thing here that should be mentioned is that OpenAI has a version of GPT-3 that does actually kind of the same thing. They haven't published how they've done that, so this is the best we have to understand that part. Right. How do you change these standard benchmarks into natural language? So here is an example of one that contains a structured problem that contains a premise and a hypothesis, and then some kind of target where you have some options. And then this is changed into natural language by stating first the premise, and then based on this above, can you conclude this, and then you have these options below. They have 10 templates for each problem, and they up to 3 of these templates change the problem dramatically. So for instance, instead of trying to see if the hypothesis follows from the premise, they are asking to translate the premise into French. And that was kind of an odd thing to do, I felt. And they don't really explain why, except I found it actually in one of the appendix hidden that they did this, but it turned out not really to matter. And fine-tuning is unfortunately an art form at this point. You try something and then sometimes it doesn't work. They have a classification scheme. I'm a bit that's written here, but it's it's presented, but it's quite unclear from the text whether this is something novel or how do you normally do classification in these language models. I think actually that's the same way that GPT-3 does, but it's not presented as such. So I'm unsure whether this is actually something new. The data sets are clustered in a rather interesting way, or that's in a way that's very essential to this work. So here are 62 problems that are first divided according to color in generative here and understanding, natural language understanding, and then it's following. It's divided into further clusters. Some of this, like there's a reading comprehension, a common sense, and a reading comprehension with common sense. They admit this is somewhat of an art form. How do you put this into clusters? And I actually think this would be really interesting to see some rigorous work being done with. Of course, in AI, clustering things is something that is very, very well known. There are standard ways to do that, and it would actually be really interesting to see. Like I can make predictions, like something like sentiments might not be something that is natural for language models, and I kind of predict that if you try to cluster this to see how close these are to each other, I'm not sure this would look at all like this. And also, it should be said that this the metrics they using to say how good is their model performing depends strongly on how many clusters they have and the exact clustering structure. I don't think the authors quite admit how important this clustering actually is. They make some, of course, when you do machine learning, you need to split into like training, validation, and test, and they do that in a somewhat interesting way because obviously they have taken literally all the standard benchmarks they could get their hands on, and so the problem is if you fine tune on these, then what do you benchmark on? And the way they do that is to just leave one cluster out and then fine tune on the rest and see how they perform on that cluster. So that means they need to do the testing 12 times, but testing is not that expensive. And they say that actually these clusters, they didn't follow those precisely. Sometimes there were some that were still relevant even if they are outside the cluster. And I think in that case they should just have made the clusters bigger, really. That would accomplish the same thing as far as I can tell. So how did they train this? Well, they start by describing the language model that they use, and to my mind, it seems like GPT-3. Obviously, GPT-3 is the model that I know best, and Google use some other models that I'm less familiar with, and they don't describe this model the base model in relation to any other models. So I would really like to know, like, what did they do different from GPT-3? And there's one thing that's trivially obvious is that they are using less parameters, 137 instead of 175 billion. But it also looks like their model, they're doing something really, it looks to me like some kind of pre-training with getting the model to understand sentences. But I can't tell for certain whether it's how new and original this is. And another thing that makes this somewhat annoying is that they have this model that is kind of like GPT-3, but they don't compare it head to head with GPT-3 in the unfine-tuned version. They do in the fine-tuned version, and then they can see it's better. But it would actually be interesting to see, like, maybe all of the small tweaks that they've made, and of course the state of the art has advanced over the past 2 years. So it's perfectly possible that the base language model outperforms GPT-3. We just don't know that because they don't report this result. They also have a description of their fine-tuning procedure. I won't go into details. It looks kind of normal. I think they use some kind of tagging scheme that I haven't seen before, and it's again unclear to me. Is this actually original, or is this like? I don't think people did that when GPT-3 was first created, but is that like how everybody does that now? I don't know. And of course, the length of both the input and the output is set to these lengths, and this is something that I feel is very important because for practical purposes this matters a great deal. I describe how long time the fine tuning takes, and 60 hours. It's not that much, and of course TPU v version 3, that's like so last year, right? Now everything is measured in exaflops, and I can't even remember how many an exaflop is. So the results, here you can see the results as presented. Like we have GPT-3 with 0 shots, GPT-3 with few shots, and the new FLAN model. And in general, very often it outperforms. It's certainly better than the 0 shot GPT-3 in 20 out of the 25 tasks, and also even better than the few shot performance of GPT-3 often. This instruction tuning is a substantial improvement in general. But it kind of depends on precisely what task. Some tasks are almost instructions in themselves. Like the classical example of a task that is, it would be continue this sentence. That's something where giving instructions to GPT-3 doesn't really make sense because it's what it does. By default, GPT-3 just continues the sentence, and if you have something where the task is to continue a sentence, you don't need instructions. It just does it. And some of them are very much unlike that. The kind of conclusion is that if the instructions are redundant, then instruction tuning doesn't help very much, but it does help a lot in the other case. They have an interesting idea for how to make 0-shot learning, where you just get the problem, and few-shot learning, where you have like a few examples. And that's by automatically generating those from examples and not answers, using what they call exemplars. And that's the simple idea is you just take one example and then you record the output, and the output is probably quite bad because that's 0 shot in the first time, but then you add that to the prompt. So now you have one shot, and then you get in something new from that, and that gives you, then you have 2 shot, and then you continue to do that until you don't have more space in your prompt. And that's a technique that seems to improve performance substantially, especially if it's like something where there's complex output. We also notice that the standard deviation, the difference between how well you perform on different examples, is just lower. So prompt engineering, which will often have this effect, is less important. In practice, this can be automated, and I think this is, to me, some kind of hint that the architecture of transformers just isn't powerful enough. Like this is something that you put on top of the transformer architecture to make it to focus its attention on precisely the kind of thing that you want with this particular prompt, and seems like something that a smarter architecture than transformers would be able to do itself without having to add this. How does the performance improve when you add more of these clusters gradually? Well, here you can see a graph with how many clusters you've used. They don't show it for 0 clusters, and that's a bit sad. actually they kind of do here. This here is the base model, so they do in fact put that on these 3 lines, and you can see it's actually a bit funny that for 2 of the tasks, the just fine tuning on one cluster decreases performance. So the first time you start this instruction tuning process, you get slightly lower performance. But then as you add more and more, you can see the graphs just continue going up, and it seems like they obviously chose 62 tasks because that's all they had. And if someone sits down and just writes some more tasks, some more benchmarks, it seems quite likely that they would just be able to increase this curve further. So it's basically bottlenecked on the availability of benchmarks. Yeah, the only one that doesn't seem to help immediately is sentiments. So how does it scale with increasing model size? Well, if it's something that has already been seen, then the performance seems to increase very little as far as I can tell. That's actually somewhat strange that this model doesn't really seem to benefit from more parameters. But if you're instruction tuning it, then it seems to improve very much. But this is only on tasks that's seen during instruction tuning. So that's kind of what we would expect. That the more like you get a bit of an improvement as you add more examples. That seems very reasonable. But on the other kinds of tasks, the kind of task that you haven't seen, we get a much more interesting. Like first, you fine tune on something that is not what you're trying to do. If the model is small, then that is just bad. If you have a small model, you shouldn't fine tune on other kinds of instructions. But it seems, as you can see here, at this point, once the model gets above this particular size, then instruction tuning starts to help and starts to help dramatically. So this entire exercise, if you go back a couple of years, back when the largest models were 8 billion parameters, back then this approach just wouldn't make sense in general. The model was unable to learn what instructions mean and what helping mean. And apparently once you get above this level, then the model becomes smart enough to find some kind of, like, this is mostly my interpretation, that it becomes able to figure out, okay, we're trying to follow instructions, and instructions are so it becomes more helpful at this point once it gets smart enough here. That's all for today. Thank you, and see you next week or next time.